I'm going to talk a little bit about tensors because as you have noticed already, they are extremely important mathematical objects in physics. I can just, you have already seen the metric tensor. And perhaps you would not like to know more what tensors are in general, so that you can also understand better what the metric is and what it is doing. But keep in mind that there are also very other important tensors, such as, for example, the electromagnetic tensor, which is one of the pillars of electrodynamics. And for example, another one is the stress energy tensor, that basically describes fluids. And these are all tensors, all three, so also the electromagnetic tensor and the stress energy tensor are tensors that we are going to meet in the course of the lecture. So keep attention to what I'm going to say now, because it's if you have it clear, many things are going to be trivial in the following videos. Okay, good. So let's start to understand first of all what vectors are. Well, they are a generalization of simpler mathematical objects, such as, for example, scalars that have zero indices. A generalization of vectors that have one index, right? This is, for example, A, this is AI. Of matrices, a matrix has two indices. And you see where I'm going, to tensors that has n indices. So you see, we are going a generalization of this sort, but keep in mind, and I want to be clear on that, tensors, if you have a tensor of rank 2, we're going to see what the rank is. So if a tensor which is a 2 by 2, which has two indices, such as, for example, the metric tensor, it has two indices, okay, and this is a matrix. So a tensor can be a matrix, but not all matrices are tensors. Okay, this is very important. That's a key difference between the two. For example, we have also seen the Lorentz transformations. This is a 2 by 2 matrix, but this is not a tensor. Okay? And here we understand why there is this distinction. It is hidden in the definition of the tensors. They can be very general, and as general as it is, you can define them as a mathematical object that obeys certain transformation rules. Very generic, but there is a key ingredient, which is obeys certain transformation rules. That, for example, in the case of the metric tensor, the rules that the metric tensor had to obey are those given by the Lorentz transformations. Okay, this is the key difference between matrices and tensors, for example. So in this case, the Lorentz transformation is the transformation that the tensor, the metric tensor, has to obey. Okay, and we can rephrase this definition, and we can say that it is a mathematical object which whose components have certain transformation properties under a change of coordinates. And perhaps this is more clear. You can better see the link with what we have done during the previous lessons, and it is a more mathematical and abstract definition. And again, you see that it has the components, and they have to obey certain transformation properties under a change of coordinate transformations. Okay, good. Let's start now to find some characteristics that this tensor have, and the most important one that I already mentioned before is the rank, which is nothing but the number of indices, brutally speaking. Okay, in effect the metric tensor is of rank 2 indices. I can give you another example. For example, whatever tensor, whatever B is, I, J, K, 3 indices, it has rank 3. Okay, and it can have m to the power of n components. So this is a cube, okay, and it has m to the power of n components if it's referring to an m-dimensional space. Let's write it like this. If n-dimensional space, then it has m to the power of n components. That's clear. So it's a cube of this sort, of m times m times m. Okay, therefore that's the number of components that this tensor is composed of. Good. The rank can be a little bit more complicated, if you wish, than that, because we can distinguish the components into different categories. And in doing that, we define tensors of different types. Then we indicate in this way: tensor of type, I used R and S, okay? Where with R we indicate the number of indices that are in the upper part, and we call them covariant indices, and they are up. Whereas S is the number of contravariant indices, and they are down, they are in the lower part, down. Now and this refers to something that I've already mentioned when we have these indices up and down, when I made this other lecture about linear algebra. Okay, I'm coming back to that. Don't be scared by that. Okay, but just keep in mind that the rank that we can call, for example, if it has a rank n, okay, this is given by the sum of these two different indices. So that's the number of indices that are covariant, and this is the number of contravariant indices. An example might be, I don't know, another tensor that now I call A, that has 2 indices below and 1 above. This guy is of type 1, 2. It has 2 indices below and 1 above. Later we are going to understand what this means. Okay, now just keep in mind that the rank can be split in two parts, up and down, for the indices that are up and down. Okay, so this guy is of type 1, 2, rank 3. Rank 3. Or you can also say of third rank. Okay, very good. Let's continue. So we have seen which kind of properties the tensor has. What is the very generic definition that we can that characterize them. Let's start to enter into more details now, and let's give a look at tensors of type 0n. Okay, so you see it is a tensor of rank n, and they are swallowing only vectors, so they have all indices below, and therefore they are all swallowing vector with the indices above. Now I'm going to show you. So this is going to be a linear mapping. This is a linear map that goes from R to M times R to M to a real number. Now I'm making I'm making them to go to real number and not to any real number, but to Lorentz invariant number. Lorentz invariant values. Why is that? Because now what we're doing, we are dealing with physics, we are dealing with Lorentz transformations, and whenever we want to compute some properties of a physical object, we want to find the intrinsic properties of the object. So, for example, the length of a stick, okay, such as for example, the intrinsic property let me rephrase it. So we are going to deal with tensors that are kind of linear mapping or multilinear mapping, because you see I'm kind of as an input it has more vectors, but I are throwing to a results Lorentz invariant values, because Lorentz invariant values are those that are carrying the physical quantities associated to objects. Okay, because they are intrinsic properties, they are the same for everybody, no matter what is the frame of reference of the observer. Okay, an example, so it's a linear mapping. I already mentioned that, but I mention it again. So if n is equal to 1, it means that is a mapping that is linear. So it's, if we are giving an input, as an input only one vector multiplied by a scalar, this is going to be ATV, and it's distributive. It has the distributive property. So therefore, if I'm giving a vector which is the sum of other two vectors as an input, then this is going to behave like that with respect to this operation. Okay, and here I used a as a real number, and if I want, I can write it like that. So it's swallowing only one vector, and it is going to a real number. You see, that's something that we already seen. Okay, so it's a linear mapping. It obeys certain transformation properties. In our case, the Lorentz transformations. Okay, and M is clearly the dimension of our space, and if we are thinking about the tensor matrix, the metric tensor, that's equal to 4. 0, so 1, 2, 3, 4, which stands for time, x, y, and z. So in our case is 4. Okay, good. Let's continue and let's give a look. Since I mentioned the metric, let's give a look at the metric tensor for what it is from a mathematical point of view. It's a tensor of type 0, 2. Okay. So example, the metric tensor, which is a bilinear mapping. We have already seen that goes from R4 times R4, so it's swallowing two vectors, and it's throwing a real number. So you see it is a bilinear map. A bilinear map. and it's associated to the scalar product as I've shown you. So we have seen that the metric tensor, when applied to two vectors, it coincides with the scalar product that's written in an explicit way with the Einstein notation. Looks like that, equal to A, with A being a real number. Okay, I'm just putting the metric into the context of vectors of all tensors. Okay, let's move on and let's give a look at another example, and let's take the tensors of type 0, 1. What are these? These are the one forms that are also called dual vectors, that are also called contravariant vectors. Contravariant vectors. Okay, so what are they? Look, you already understand what I'm going. This was a bilinear map, because there was a 2 here. This is a linear map. So it is a linear map, and let's call it P, for example, that is going from R to M, so it's swallowing as an input a vector of size M, because it is living in a vector space, in a m-dimensional vector space, and it's returning a scalar, and I define it as PV equal to A, with V belonging to the vector space, as I said, and A being a real number. Right? It's just a linear map. It's just, as I did with the other one, could be linear map, bilinear map, trilinear map, and blah, 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 and so on and so forth. In this case, 1, and it's only a linear map. Good. What is the meaning of these objects? Let's give a look. Let's start to dig into the details. So as I said, it's defined like this, is PV. This is a vector that now I can express as a linear combination of the basis set that I've chosen to describe my vector space. And therefore this is going to be V alpha, E bar alpha. You see, Einstein notation, this is the vector V expressed as a linear combination with the coefficients multiplied with the basis set that I've chosen to describe my vector space. P is a linear map. This is a vector, but this is a scalar, and what I can do is to bring the scalar outside my map. Therefore V alpha, P, E bar alpha. But what is this? That's the mapping applied to the basis. What is it going to give me? It's going to give me the component of the mapping P. P alpha. Okay? That's the meaning of it. We are back to the scalar product. So we have a scalar product between a vector V and a one map. And to one form. Okay? You see, index up, index down. Good. Therefore, V corresponds to column vectors, and this guy here, P tilde, corresponds to row vectors. Okay? And again, look, it's not, when we make this operation, it's not, again, I stress it again, it's not that we're just flipping one vector and the components are the same, but this operation is going through the metric, as I already mentioned, and as I'm going to show you once more later. Okay? So, that's the meaning of the types 0, 1. And there are one forms, dual forms, and contravariant or contravariant vectors. We can call them like that. Good, let's see if we can define a space to which these objects belong to. And let's see if we can, therefore, define a basis set for this sort of row vectors. Okay, so we define the basis for the one forms. How do we do it? What do we want to define? Well, we want to define an object, so a basis set that I call omega tilde alpha, that I call it like this. Okay, now I'm creating this sort of objects, and I want it such that if I have my one form, I define that I obtain it as a linear combination of the basis set, exactly as I would do with a vector. We already seen that a vector v can be written as the linear combination of its coefficients I times the basis e. Right? Remember, this is the symmetry again, repeated indices, and I just want to do the same in full analogy. That's a definition. I don't know what this guy look like. I don't know how the bases look like, okay? But I want to find out what it is starting from this definition, okay? So I'm building up a mathematical objects with this construction. Good, let's see. Let's ask then ourselves what this omega tilde alpha is, okay? And let's start by applying our one form to this vector. Okay, so I'm just going to apply this construct up here. Okay, we know that is this mapping, and now I'm just going to apply it to the vector. So what I do, I just plug in here my definition of the one form based on this definition. I'm going to plug in the vector as constructed in this way. So I just plug in here these two terms. So first I start with this one, p alpha omega tilde alpha, which is this guy here. And then I have v bar, which is this one, vi e bar I. Okay? Good. Now what we have? We have that this is a linear mapping itself, therefore I have a vector, I have a scalar multiplied by a vector, and I can pull it out. Therefore I can have p alpha, which remain like this. I have the vi, I can bring outside, and then I have this guy, which is again a linear mapping, and therefore I can write it like this. But now again, what is it in analogy to the vector? I am this sort of mapping applied to this vector. Okay, what is it going to, sorry, to this vector, which is one of the basis set? What am I going to obtain? We have done it already n times. I'm going to obtain the coefficients of this basis. And therefore, what I get, it's, what is I is a bit, let's call it beta, I mean, it doesn't change, but since I was using Greek letters, I'd like to stick to Greek letters, okay? Good. So we have this, and we have p alpha wait, sorry, okay, right, okay, right, okay, so good, sorry, okay, so this is all correct, and we basically arrive at the definition by starting from this side and plugging in the definition of how we want this object to behave, okay, in analogy to the standard vectors, and we arrived up to here. But then we know from what we have seen before that PV must also be equal to V alpha P alpha. So if I want to be consistent with my notation, please introduce also the tilde here, here, and here, and everywhere, here and here. Okay, good. Anyway, So if I'm starting by introducing my notation here, I arrive up to this point, and then I need this object to be equal to this one. Otherwise, I would break its very essence, right? And therefore, what I do, I am going to impose this derivation equal to this part here. Let me write it exactly in the same way. P alpha, P tilde alpha. This must be the case. Now I want that to see what is the omega such that this operation becomes like that. Now look what's happening. We have P alpha, sorry, I forgot whether that's the component. Ah, God, like that. Okay, now it's fine. Sorry if I messed it up. So okay, because this is the operator that I call with the tilde, but this is a component. I'm already making the people understand that is one form because the index is below. So I am not going to introduce the index. That's what is usually done. Okay, here I messed it up, but that's what it is. So don't put the tilde there, but it has to be here. Okay, good. Okay, perfect. Now we have it. So what we need to have is that this beta actually becomes an alpha. Okay, you see we have it here and we have it here. Therefore, this object here, to have this sort of change, must be the delta of Kronecker. If we have that omega tilde alpha is equal to delta alpha beta, then the operation is done. Because you know that the Kronecker delta, whenever it's applied to an object, is going to change the index from alpha to beta. So beta to alpha, sorry. In fact, if we do that, I just do the operation here. We have P alpha, which is not touched, V beta, and then we have the Kronecker delta beta alpha. Okay? You see the Kronecker of delta is acting on beta, and what is left is the index alpha, which is above. Therefore, we find out what is the basis set that describes the one forms. And if you want, the Kronecker of delta, if you want to link it to the coordinates, is the derivative. You can write it as the derivative of x alpha over the x beta. So you see that these basis set are actually the derivatives of the coordinate of the vector space. Okay, that's their meaning. Last step. Let's give a look at how n is working with respect at the metric tensor, how it's working with respect to the indices. So we have nu, and this guy converts vectors into one forms. Okay, it lowers the indexes. Okay, I've already shown you that, but I want to have something self-consistent about tensors and being it complete. Okay, so that's what this guy is doing. And to do that, what we do is that we define an object, which is the matrix applied given a fixed vector, and we let one slot free. And we define it P tilde with one slot entering. Okay, so we are basically defining this object as this guy here. I have one slot free, and I just let P work together with nu to obtain this P tilde, which is a linear map. So we are converting a bilinear map into a linear map, as I already discussed. To have the components, as usual, you just plug into your linear map the basis set that you have chosen, and you find out what is the coefficient of that mapping. Therefore, if I want to compute what is P alpha, which is P tilde E bar alpha, as I just said, which is equal, now I'm using the definition, so I'm using this definition here, which is what? It's nu p bar, and then the input that I'm plugging in here, right, of E bar alpha. Then what I do, I express P as a linear combination of the set, on the basis set on which it is defined. Therefore I have nu P alpha, the index is up because it's a vector, E bar alpha, but let's change index because I'm already using alpha there and I don't want to make confusion. Again, nu is a linear mapping, therefore I can take this guy outside because it's a scalar multiplied by a vector, and I obtain P beta nu, this remains inside, and then E bar alpha. Again, what I have, a bilinear mapping, and I'm introducing the basis on which this guy is constructed, and I'm getting in this way its components, which are beta and alpha. Now this tensor is symmetric, therefore I am free to change the indices. So now you see what I have on the two sides. I have a vector with the index up, to which I'm applying the metric tensor, and what I get is a one map with the indices below. Okay, you can see that here I am making the contraction between these two indices, and I'm left with alpha. Okay, good. Now let's go, we went from the generic, from a very general case to a very specific case. Let's go back again to a general case with tensors of type Mn, because so far we let them swallow only vectors, but I can also swallow at the same times covectors, or if you wish, one forms and vectors. And these are what? These are, you already know, linear mappings of M1 forms and N vectors. Okay, good. An example can be 0, 1, and this is a 1 form. Another example is 1, 0, and this is a vector. Okay, so you see in the end they are all the same object, they are just reshuffled it a little bit around through the metric, because the metric, as we have seen here, can rise and lower indices. And if we take a tensor of type n m and we apply the metric, we can lower indices, and we get a new tensor with m minus 1, and I'm lowering plus 1, because one something that was a contravariant vector or a one form up here, I throw it down, minus 1 plus 1. And for example, we can write n alpha beta, then I don't know, some tensor mu beta gamma delta equal to, look, this is sorry, this is a mu, otherwise nothing is happening. So we have mu and mu, so the matrix is lowering the index, and we have a new tensor, look, I'm saying new tensor, which is of type mu beta gamma delta, which has all the indices below. Otherwise we can also use it to rise indices, and if we have a starting tensor which is like this, we are here we lowered it, here we want to rise an index, therefore we go from here to here, plus 1, and then there is the minus 1 that we took from below. And for example, we can have nu alpha mu and then we have a tensor with might be beta, mu, gamma, delta. And that's equal to what? Now you are experts, you're all experts. We have mu and mu repeated here, and we are going to have the alpha in the higher position. So we have beta, alpha, gamma, and delta. Keep always in mind that the order of the indices is important, okay? Because in this case, it's not, I could flip the indices because this tensor is symmetric, but there are tensors that are not symmetric, and therefore if I'm changing the orders, I'm going to change the meaning of the tensor, and we don't want to do that. Okay, so always keep in mind to keep like the position of the tensor, of the indices in a tensor very well aligned in order. And this should be all what you have to know about tensors. Okay.